Okay, here we go. Okay. Um, so Francisco, can you now see my screen? I had to change some stuff.
Yep.
Okay, awesome.
That's
So sorry for the delay, everyone. But yeah, today we're gonna I believe in practice and repetition. So today we're gonna do a few things. We're gonna pretty much simulate the electric aircraft. I didn't cover that last time, and we're gonna then cover an eVTOL simulation. So last few lectures, well, I guess the last videos we've covered pretty much how to run a 737 simulation. In the second video. Then the third video, what we did is that we went in to study the energy network itself. So we looked at the energy network. Um, in this video, we're going to look at an electric network. We're going to look at the all-electric network, which is the basis for studying things such as maybe drones, all-electric propulsion aircraft, conventional aircraft. But also in the future, you can see how this network can be modified to study hybrid electric and hybrid propulsion systems. So I'll talk today about an electric aircraft, typically a general aviation electric aircraft, modeled after the NASA X-57 Maxwell aircraft. And we're going to go through pretty much how do we define the properties of that aircraft, how did you define the network in that aircraft. I'll go into the all-electric network today, and hopefully we can run a simulation. And if you have time, I'll go into the eVTOL, how will you set up an eVTOL, which is essentially a more elaborate network. Small disclaimer. So for those on, I guess, YouTube, and obviously for those in here, the all-electric network, we're doing a lot of development to make sure to do things such as failure mode analysis, and modeling different types of uncertainty quantification when you have a partial network failure. So what you may see that I'm showing today is going to be a little bit different from what is probably going to be there in the next few weeks. But this same concept still remain same. Okay, so starting from the top of the script here, once again, your main for the average user, for the everyday user, they're not pretty much going to be touching anything behind the scenes of anything deep in the code. So the everyday user pretty much just has to write one script, right? That vehicle.play, the x57.play, eVTOL.play, list, whatever you want to call it, your script. So basically starting off here, we have a main function, right? And in our main script, it's pretty much about 20 lines long. Well, 10 lines, about 10 lines long with some comments. But basically, you first define your vehicle once again, in that function vehicle setup, right? Then you define different configurations. And does anyone remember what configurations are? Yeah, part of the flight that's on, right? So basically, exactly. So I'll just repeat what Naranjan said. Basically, configurations are just modifications or alterations to the baseline aircraft, right? So if you define an aircraft, and you have, let's say you define your flaps or your slats or any type of thrust rotor angle to be 0, you may have a different one during takeoff, right? Or you may have a different flap setting or elevator setting, and you define that by having a base vehicle, and then you use the configs to just modify and store those different variations. And then that allows you, when you're running a simulation, you can, for example, if you have an eVTOL, like a Joby aircraft, right? You can pretty much have your thrust angles at 90 degrees when you're taking off. And in transition, maybe you want to define a different configuration that has it at 45 degrees. And then in cruise, you can use a cruise configuration that has it at 0 degrees, right? So that's your configs. Then you have your analysis. So here you have, what type of analysis you're running. So you can have aerodynamics, you can have stability, you have weights, what type of energy analysis, if you want to do cost analysis, want to do noise analysis. I am actually currently right now making some small tweaks to the analysis such that by just changing one line, you can change from 2 degrees of freedom to 3 degrees of freedom, which is including stability, to 6 degrees of freedom, right? So we're trying to figure out, okay, how do you actually, if you have a eVTOL, for example, and you want to model a particular transition or a particular banking turn, it can be done now in RCAIDE, right? It's pretty cool, right? So that's what that's what I'm doing right now. Then the mission setup is where you define your mission. So here is where you specify what are the flight kinematics for each flight segment. How, if you define, for a eVTOL, for example, if you want to first take off on up to and vertically climb up to 10 feet, right? You put, altitude start 0, altitude end 10 feet, right? Then you have different transition segments you can define, and then you also have, cruise segments, etc. So here also I'm doing, the interesting thing is that all of the development within RCAIDE is very linked now. So in addition, if you can define an analysis, right, in terms of how many degrees of freedom you want to specify, in terms of if you want to do a 2 degree of freedom or a 3 degree of freedom or a 6 degree of freedom problem, the number of degrees of freedom means that you require more control variables on the aircraft, right? Maybe you want to have to control the elevator flat angle, maybe you want to change the throttle settings independently, etc. So in the future, very soon, in the mission itself, in addition to defining the flight kinematics of the mission, you can actually specify what control variables or what control devices you want to control the aircraft, right? So we're allowing that flexibility for the user in the new RCAIDE code. So so sit tight, and it's coming very soon. Then you can study different missions using the mission setup, and then lastly, you evaluate your mission in line 42, and then you plot it, right? So today we're going to talk. It is a repetition, but I think having this repetition is very important for new users, and obviously for you guys, because you can understand how to define a mission, how to define an aircraft, right? So the first thing I'm gonna do is to pretty much run this vehicle setup. Actually, I don't even need this. Huh, interesting. Some legacy code. Anyway, so the first thing you want to do is to define your vehicle setup script. And your vehicle setup, you first define your vehicle, RCAIDE.vehicle. You give it a name. It's X27 Maxwell modification 2, because there are 3 different modification. Well, there are actually technically 4 actually. Then we define our high-level properties. So we have here our mass properties. You have a takeoff weight, maximum 0 fuel, which they're all the same because of the electric aircraft, right? There's no fuel inside of it, so they're all the same. Then you have a reference area, number of passengers, and then you define your, we wanted to include some other properties such as the design Mach number and design dynamic pressure. So we just define some properties here to do some quick calculations, right? So you can do some quick calculations if you want to pretty much define some stuff. And then here's I'll use one of Professor Ansell's terms. Here's the meat and potato. Oops. Here's the meat and potatoes of it. So basically, we have a main wing, right? So once again, for RCAIDE users, you can define a wing just by lines 128 to around 148, right? So you don't have to include any additional segments, but you have the high level properties of the wing, the aspect ratio, the span, the root, the twist, etc. If it's vertical or not, if it's symmetric. So that's what you have here in lines 128 to 148. But we want to, but however, maybe we want to add or define segments on a wing, right? We want to make it more realistic. So we can define a few segments here. So I have our inboard segment, our outboard segment, and our winglet, right? So these are just additional things that you can define on your aircraft, and this will obviously affect the aerodynamics of your vehicle. And if you want to actually export it to OpenVSP or any type of CFD software, and you want the segments defined, if you want to do like some high fidelity CFD, then you should probably define segments, right? And it will export as well. And then that's your vehicle right there. So right, you can append it onto your aircraft, right? So you just sorry, that's your wing, sorry. So you append the wing onto the aircraft. Then you have a similar thing for the horizontal stabilizer. So once again, you can define the horizontal stabilizer by its a simple level, a simple number of arguments, or you can add multiple sections. For this aircraft, this horizontal stabilizer is a simple trapezoid. So I don't need to define two segments. I just define the wing by itself, right? Similarly for the vertical stabilizer, as well. So I'm not gonna go over the vertical stabilizer, but the only thing that's different is that I specify my vertical is true, right? And now my vertical flag is true. It knows that when it's doing the Fortit's lattice method or any type of discretization, it will make sure that, the Z, it really and truly, it changes the Y value to Z. So that, it goes up. Makes sense? So the fuselage, we want to make sure we get the fuselage similar to the X-57 aircraft. So in addition to just the simple design parameters, we actually specify a lot of segments in here, and that gives it the nice shape of that general aviation aircraft. So we already covered this in the Boeing 727, so I'm not going to cover it here. I think what's more important is the actual energy network, which is the thing that sets RCAIDE apart from pretty much, most codes out there, right? And that's, I mean, for those viewers too on YouTube and I guess on Zoom, that's what makes this code different, right? We spend a lot of time actually on how do you really model an energy network that is very realistic, and it is a challenging problem, right? How do you balance conceptual design with trying to include all of the different things that will really happen on the aircraft, right? So for example, I had a discussion earlier this week about how do you model if a tanker is flying. So a tanker is flying, so it's using fuel on the engines, but it's also fueling another aircraft. How do you model that at a conceptual design level? Which is a very interesting question, right? Because imagine fuel tank is going to have a different MDOT or fuel flow rate. That's going to change the weight of the aircraft. That's going to change stability. So how do you do that in a transit manner? So I think we started to figure that out, and I'm working on that right now behind the scenes. So here are some nacelles. The only thing different from this nacelle and the 737 nacelle is that I have a flag here saying flow through faults. Because the nacelle basically just houses an electric motor, so there's no air going through our nacelle like a conventional 737. So just the FYI. So I want to stop here now. At the all-electric network. So here's, I guess, the main discussion. I mean, for those who are interested in electric design, eVTOL design, etc., this is the network pretty much you're going to be using. And like I said, we're doing a lot of development on this network to iron out a lot of kinks in it to make sure you can do things such as using half a battery to power one set of propellers and the other half to power another set. We're doing some really cool things to figure out, okay, how does it really happen in reality where you have a very interesting or a very complex energy network. So first, you start off with defining your network, right? All electric. And then similar to on a fuel aircraft, when we define a fuel line, on this aircraft, because it's all electric, we define an electrical bus, right? Similar, it's very synonymous, right? In this case, however, because this is a regression analysis, I made that there's a flag called identical propellers or propulsors, and they made that equals to false, right? Obviously, obviously this aircraft, the propellers are identical, but I'm just doing this to show you that you really can actually simulate each propeller by itself. Why you would want to do that? Well, when GE tests engines, right? What they do is that they they fly like a 747 modified, and they take off one engine and put a new engine on. You can actually model that now in RCAIDE, right? Where you actually can model how a new engine will perform given the same amount of throttle, right? So those are those are the sort of changes that we made such that you can, it makes us more attractive for people to do very complex things um at the conceptual level, right? You don't have to wait till you have to you put it on an aircraft to get a simulation or result, right? So the first thing I do here is I define my batteries. So I define my battery. Just have one battery pack made of a certain amount of cells in series and parallel. I'm not gonna cover specifically the distribution, but it's in a cited paper from NASA where they actually tell you how many battery cells are within each battery module and how many battery modules are within each battery pack, sorry, and then how many battery cells are within each battery module. So I'm not going into that. The only slight change I made since the last discussion basically is that you know decided well, now I will mention that because this is going to change very soon. Anyway, so we define our batteries, right? And we append our battery onto a data class called batteries that is appended onto the bus. So in a similar way, how we create like a fuel tank, and we append that fuel tank to a data class called fuel tanks that's on the fuel line, similar for the battery in a basket of batteries, and you put it on the bus, right? And this now actually allows you to simulate aircraft with different batteries, right? And if you literally can try different battery arrangements and figure out, in flight, if you want to change instantaneously on the aircraft simulation, change out one battery for the next, you can easily do that now in RCAIDE, right? So that's the battery definition. Now, we have two propulsors, right? We have a starboard propulsor and a port propulsor. And like I said, a lot of folks may be questioning, well, why call it propulsor and why not just call it a turbofan engine or a propeller? And the reason is that, yes, for a conventional 737 aircraft, the propulsor only has one component, a turbofan engine. But for an electric aircraft, you may have a motor, a propeller, or a rotor, or a prop rotor if it's a Joby aircraft, right? You have multiple different components that are actually working together to create thrust. So that's why we group them into the term propulsor. Does that make sense? Okay, so we have a starboard propulsor, and this starboard propulsor has on an electronic speed controller, which I define. It has on a propeller, right? And in this propeller, I basically define some properties, the number of blades, the hub radius, the propeller design performance at cruise. I give it an airfoil I want to design my propeller. And then you have a nice line here in line 528, and that's where the propeller is actually being designed. So this is simply using a formulation of blade element momentum theory with a vortex wake type of coupling, and we are actually designing the propeller based on the user's requirements. Make sense? So we have our starboard propulsor, and we append it onto the rotor. So 503 is where we append the ESC to the propulsor, and then 529 is when we append the propeller onto the propulsor, right? And then the last one is the motor. So in this case, we define our properties of our motor first. So an arbitrary motor, right? So we define our properties, and then we actually can use this function called size optimal motor to design a motor that is optimal for that aircraft based on other properties, right? So this motor, if you think about it, the optimal motor matches the torque from the propeller. So essentially for the motor design torque, we just use literally the propeller design torque, right? So we design it for a particular condition. And then we just run this script, size optimal motor to pretty much fill out the rest of the properties. Now, bear in mind, this is not the only way to design a motor. I think there are 4 or 5 different ways to define your motor in RCAIDE. We just use the one called size optimal motor. But You can use there's a NASA correlation model in here where you essentially NASA had wrote a paper on motor torque versus RPM, I think, or something like that. And if you specify the motor torque, it gives you back what the properties of a motor, right? So it's not the only way to design a motor in arcade, it's just one of the ways. After that, we know that we have our properties of a starboard propulsor. You append it onto, the basket of propulsors. So that basket now of propulsors has in one propulsor called starboard propulsor, right? So that's one on one side of the aircraft. And then the port propulsor, I'm not defining again. So what I do is that I pretty much use this Python function called deep copy. So I just copy the propulsor that I already created. I mean, the electronic speed controller. But all I do this time is that I change the origin, right? It's on the other side of the aircraft. So I define, so I have ESC2 and pretty much append it on. Then I do the same thing for the propeller and I do the same thing for the motor. Note that in line 560, you may want to change the rotation of the propeller. You may want to have all the propellers turning against each other, or you may have the propellers turning all clockwise or all anti-clockwise. You can do that by a simple flag, right? And this is very useful if you want to have, if you have, let's say, the X-57 modification 3 or 4 on that aircraft. It has a whole series of distributed electric propellers. So you may want to modify that such that you can increase the amount of wing loading or decrease the amount of swirl, etc. So you can do all that stuff now with arcade, which was not possible before in 12, so 12, right? So that's the case. And now, once you finish that propulsor, you can pretty much append it onto propulsors, right? And also you append, so that's pretty much the propulsors. And then we want to add a few other things, right? You may actually have on that electrical bus, you may have a payload, maybe some avionics or something. So you can append pretty much a data class called avionics and payload, right? If you have something else running on the aircraft that what drives that, how much power it pulls, you can just append it on. So when the bus is simulating, when the energy network is simulating, it is actually also keeping track of how much energy is being pulled from these components, right? So, and that's your vehicle, right? We define the fuselages, we define the wings, define the energy network. That's pretty much it. And then the cells. Right? So that's the whole vehicle. In this aircraft, we have only one configuration. We didn't really simulate any flaps or anything, so just only one. But like I said, for an eVTOL, you should, you probably should have multiple configurations. Each unless you're taking off and landing normally, then it's not an eVTOL. But when I'm designing eVTOLs, for example, let's say my stopped rotor. Look, let's look at our stopped rotor. It's a way more complicated aircraft, but my stopped rotor has the stopped rotor is a very interesting aircraft because I don't need to change in the configurations. I'm not changing the thrust angle. I'm just turning on and off a particular bus. I have a lift bus and I have a forward bus. I have a bus that is for the lift rotors and I have a bus that's for the forward rotors, right? So you pretty much just have to one flag, boom, turn it off. And this is something that's new that we developed in arcade now, whereby you don't have to, toggle between all the different components, just one line. Obviously for transition, you need everything on, right? Yep.
Could you also just do this for like flaps and stuff? Or would you need a new configuration, or is that
for flaps? So yeah, good question. So the question was, do you need to do this for flaps? So yes, you can actually put flap angles in here. It is done. I think the Boeing 737 aircraft has flap angles in here, right? So you can actually so this is like cut back, short field takeoff, takeoff. You can set all that stuff in here, right? So just some options.
But it's still the same configuration, right?
No, so
Or
so
that makes a difference.
so yeah, it missing. So what it is, I take in the vehicle itself, right? So this configs.setup takes in vehicles, then it creates a base configuration and it saves it to this class called configs. Then it uses the same base configuration, and changes the name to cruise. So now you have a base config and a cruise config, which are the same.
Yeah.
But then for this one though, it takes the base configuration, right? And it modifies it, right? And stores it onto the config. So at this point, you have 3 different configurations, right? And you have the same, so right now this one has, well, 6 different configurations. And in your mission setup, if you see here, you can actually change exactly what configuration you're using for each flight segment. Right? So that's what we're doing here. Yeah.
Probably then for the tanker, we should also add the configuration where it's actually pumping the fuel out because it will have extra drag and stuff from that thing at the end.
Yeah. So the question was if you want to model a fuel tanker, exactly. For the fuel tanker, in that configuration, the only thing you have to put is I already placed a tag called secondary fuel flow, just make it not zero, right? And it would simulate everything for you, right? The aircraft would change accordingly. The performance of the aircraft, I mean, it wouldn't really change, but the weight would change significantly, and that would change the stability, etc. So when I have been developing a lot of these methods, I've been really thinking about, okay, what's the easiest way for the user to change all these different things? Okay. Okay, so with that being said, I think before even going into any simulations, I want to go into this all-electric network, right? So the last time we went through the fuel, we went through the turbofan engine network. Here's the all-electric network. And the reason I'm going through this is, well, 1, for repetition, but 2, to show you how similar it is, right? So for this network, we've seen this before, you have this defaults, which is not really anything. Everything really happens is in this evaluate thrust, right? In a turbofan, you evaluate some thrust, similar thing in here, right? So, like I said, there'll be some slight changes in this network, but it still will perform the same, basically. In this network, it goes through first for each bus, right? And yes, you can have multiple buses on an aircraft. Why? If you have an eVTOL, like a stopped rotor aircraft, right? The propellers will like to operate at the propellers will like to operate at a different voltage than the rotors because they're flying at different speeds, right? Rotors is for slow flight, propellers are for fast flight, right? And therefore, it might be better for you to separate the buses, right? And that's actually what already happens on the aircraft, right? You don't have 2 buses on this aircraft. I mean, you don't have 2 buses. Sorry, you have 2 buses on a stop rotor aircraft, right? So for each bus, if the bus is active, it does a whole simulation. If it's not, then you're good. You skip it, right? Because like I said, for eVTOL, when the eVTOL is climbing or stop rotor is climbing, there is no the propellers are on, so you don't have to run a simulation. Doesn't make any sense, right? So what we do is that if the bus is active, it runs the avionics power, the payload, it computes the bus voltage, which is set by the user. And then what it does is that you first determine, well, is the bus recharging or not? Because the bus can be recharging, right? If the bus is recharging, it pretty much it pretty much computes the power from the payload, the avionics, as well as the charging power, because it's charging. And then it just sets those variables as inputs to the battery. And then the battery then you run the battery simulation, right? So that's what happens when the aircraft is charging. When it's discharging, however, or in nominal flight, you first compute the performance of the propulsors, right? So these are the motors and propellers or rotors, whatever's in there. And for that group of propulsors, you're going to get a thrust, a power, and I guess the current, right? How much current is being drawn in from these components, right? And then you pretty much you add them up, right? Because you can have different groups of propulsors. Then you start to package these components for the battery, right? So once you have an idea of the avionics power, the payload power, then the total ESC power, the total power that is drawn by the electronic speed controller. And remember the electronic speed controller. Oh, I see your hand say 1 second. Remember the electronic speed controller is pulling power, is delivering power to the motors and propellers, right? Basically, you add these three powers together and you add these three powers together and you assign it to the battery. So you know which power is being drawn from the battery, right? If you know the power drawn from the battery, right? You know the current drawn from the battery, then you can run your battery simulations, right? So herein, if the user now wants to use any type of battery simulation model, right? It can be equivalent circuit model, it can be a DFM model, it could be a semi-empirical model. You can actually define what type of battery simulation you want to run, right? And not even have to touch the network because it's all, the battery itself, pretty much everything lays on the battery side. So we wrote the script in a way such that you can think of the networks as the glue, right? You don't have functions in here to compute propulsion and thrust. You just have this one line that calls functions that compute propulsion and thrust. You don't have the function that essentially simulate the battery. You just have one line that takes in all the components required to get that battery simulation and run it, right? And then once you finish, you just package everything and send it back to the optimizer or the mission solver, right? Now, some of you in here study batteries. So if you were interested in figure out, where this 134 line goes to. Actually, before I continue, Sai, do you have a question you want to ask?
Yep. Can you hear me?
Yep, I can hear you.
Yeah. What about if you want to recharge during flight, some sort of regenerative mechanism, if it exists, how would we go on about like is there a way we can solve that problem?
Yes, you can. During flight, you see this line I have highlighted 128.
Mm-hmm.
I think you actually mentioned this before, and I thought about it, so I was trying to figure out how to put it in. We just have a charging power, right? So what
Uh-huh.
happens here is that um it's very tricky because you have power being drawn by your propulsors on the bus, but
Yep.
also you have power being for charging. So essentially, the only way your battery could recharge on the bus is if you have more charging power than power required, such that when you run this equation here in line 132, the power is negative, or well, it goes into the battery, right? So it is possible, but it only happen if pretty much you have something else that's powering your whole system and also pouring out battery. So the way how it's coded is possible. I think Edwin is also working on stuff if you have, let's say, a turbo shaft powering a battery, but I guess
Mm-hmm.
that's another conversation. But yeah, technically speaking, mathematically it's possible.
Okay. Got it. But like I just wanted to know out of curiosity, how does it happen in real life? Like, does the
Well, we're
same
gonna find
battery
that
pack?
out. We're gonna find that out in the next few weeks, right? Hopefully.
Okay.
At Argonne, right? Like there are things
Yep.
that I think like is very critical for us to get an understanding um I think our trip to the national lab, we can ask those questions. So just keep those questions, you know, somewhere handy so that we can actually ask them when we get there.
Got it. Got it. Thanks.
Okay. Yep. So, um, we have about 14 minutes left. I'm actually not going to run the simulation. It is a bunch of plots. We've seen it before. What I actually want to do, however, because we have folks in here who study batteries, is to go a little bit more into this battery simulation. what's happening? What's actually happening here? So, this battery dot energy calc, right? If you see battery dot something and you have a brackets, that means that there's a function that is linked to the argument battery, right? So, because I know where it is, I'm actually gonna go to it right now. I'm gonna go to energy sources batteries, lithium ion, NMC. So when you're running that energy calc function is located in the it depends on what type of battery you have. All batteries have an energy calculation, but because the scripts already know it's Python, it already knows that we assigned it NMC battery cell, which is a lithium nickel cobalt oxide battery cell. What we have is that this energy calc, and I hope you guys appreciate the level of notation we have here, right? We actually can tell it tells you it's specified. This script pretty much specifies the discharge and specific energy characteristics of a 18650 lithium ion, well, NMC cell, and it tells you the sources of the model we're using, right? So right now here, this is pretty much a model for, we have the discharge curves, we have a convective heat transfer, the thermal conductivity, everything is in this model. There's a source for it. We also have some defaults, which I'm gonna go through, but the energy calc we have here, it takes in a whole bunch of properties, right? So we have the conditions from the battery cell conditions, but also, these two guys here that we just packaged, right? This is pretty much the power and the current that we had just calculated from the propellers, right? So that's IBAT and PBAT, right? It also takes in the thermal management properties as well, properties of the heat exchanger system and heat acquisition system. And then it does some calculations, right? It calculates the internal resistance, it calculates the property, the current within each cells, the joule heating, the voltage, the underload voltage by reading off this pretty much this function computes it using a lookup table. And then we get the properties of the individual cell, and then to get the pack properties, we pretty much multiply it by a number of cells or whatever, right? So this script is still under development, but the point is that even in your all electric script, this energy calc, this energy calc function, it calls the energy calculations for whatever type of battery you have, right? So you have lithium ion, you have LFP, we have lithium sulfur batteries, we have lithium air batteries, and each of them, not this one, but let's go to LFP. Each of them have an energy calc in it, right? So we're still, I think generic one has one too, yeah, energy calc, right? So it tells you, what energy calc, yep.
Type of battery modeling is defined inside each type.
Yes. So the question from Mateo is if the type of battery modeling is defined within each type of cell? Yes. So one of the things we may look to do is, well, can you now not only specify what type of battery cell, but what type of modeling, right? If you want to use PyBAM, which is a tool developed in the UK to do more high fidelity modeling, or if you want to use a lookup table like I had, that's what you can do in this in RCAIDE. And the beautiful thing about it is that you don't ever have to touch the network. You just have to edit the battery functions, which are in the battery script, right? So that's the beauty of it. So I mean, we're doing a lot of battery stuff in our group. So I suspect a lot of stuff is gonna change in here, right? Like what types of energy calculations? How do you modify the energy calculations? Then can you compare different models, and how does that compare to experimental data? Right? Okay, so it's 4:51. I want to stop here for no. So you have another question?
Oh no, I forgot to.
Okay,
No,
no worries, no worries. Yeah, so I'm gonna stop here for now. I'm not gonna run a simulation because you can run it yourself. It does the same thing. The code currently is under a lot of development, because we're trying to prepare it for our launching in well, myself and Professor Smart, we're trying to prepare it for our launch in aviation. So what you see right now is just a rough version of what's going to be there, but we're going to clean it up and make it nice. Some students here are also working on a nice GUI. So, which I saw recently and it's looking really, really cool. So I'm really excited about this GUI. Francesco, do you have any questions?
Yeah, I had a question about the configurations.
Yep.
So if you have an eVTOL that tilts the propeller, is a tilt angle, I mean, one value of the tilt angle like a configuration or not?
Yes. Very good question. Up until last night, literally, what you would do is that you would specify in your configurations a tilt angle, right? So, if you want, if you have like 8 propulsors and you know they're going to tilt at a particular angle, you just specify each propulsor you just specify the angle of each propulsor, and then you can call that, let's say, transition phase 1, right? And I had, for example, when I was doing the Vahana aircraft, I had like 4 different configurations. One was at 90, one was at 75 degrees, one was at 45 degrees, one was at 25 degrees. I think the last one was at 0 degrees. And I specified different flight segments, and then each flight segment I assigned different different configurations. And I said that I was up till last night. What I've been working on with some of the folks here is that we've been thinking hard about how do you now make, instead of specifying it as a configuration, can you put it now in the mission solver so it solves the actual the optimal flight angle for you? So I think we should hopefully have that very soon. And that just gives the user 2 options, right? I mean, I know for a fact, we spoke to some guys in the Army a few years ago. They do specify a particular angle and it just flies through those phases of set angle. But someone may want to specify a variable angle or a variable thrust change. So we're trying to make that possible as well.
Okay. Yeah, that's very cool.
Okay. Any other questions?
Thanks.
Okay. So I think we're going to close off here for now. Next week, I think maybe the last one. I think everyone pretty much knows how to run arcade now, or should. So I think we're gonna do one more one. And in that one, we're gonna do an eVTOL. Right. So now it's gonna be a little bit more complicated, but I think given what we've had so far, everyone should be able to follow along. Okay. All right. So I'll see everyone later, and I'll stop sharing right now. And I will close off the session. All right.
Bye, everybody. Take care. Have a good
care.
weekend.
Bye bye. Have a good weekend.